Today we're going to talk about the chemistry of combustion. We're going to talk a little bit about some of the evidence that's left behind in arson, but there's a whole lecture on that, on the physical evidence of arson. We'll talk a little bit about the chemistry. Explosives, and since my background is in explosives, high explosives, and worked for the site that refurbishes the nuclear stockpile for the nation, I'll talk a little bit in general terms about nuclear weapons. Again, those are always a concern of folks in the forensics area, that you might find yourself working in an area where you're in counterterrorism. And what kind of evidence would you be looking for in those situations to stop like a weapon of mass destruction attack or maybe a biological weapon attack? And so there's always got to be some sort of dispersant, or if in a detonation, there needs to be some sort of evidence that you would collect. And so we'll talk a little bit about that today. Not your typical lecture. So combustion is the second most common forensic analysis behind drug and toxicology. So it's either arson or fire. There's lots of fires, and so trying to determine whether it was arson or not is an important role for the forensic scientist. We need to talk about combustion basics and look at some of the calculations that go behind that. So we're going to review some of your stoichiometric techniques that you learned in Gen Chem 1. It's always good to review. And then we'll talk about fires, combustion to explosion, where we transition from burning to a new word for you, deflagration, which is vigorous burning, and then to detonation, okay, which you've heard of. So what is an explosive detonation? We'll discuss that. And then we'll get into how we turn, say, a chemical explosion into a nuclear explosion, like what makes the difference. Okay, so let's talk about the fire triangle. Have y'all heard of the fire triangle? I mean, does this make sense? What do you need to have a fire? Don't look at your notes. Fuel, yes. Heat, yes. And oxygen. Okay, good. Because we have fuel and oxygen all the time together. And our atmosphere is 20% oxygen, and all of these things are combustible. So why do they not burn? Well, there's activation energy. You learned about activation energy when you had that little chapter of kinetics, or like a portion of a chapter of kinetics. You had this activation energy barrier. And so that's what you need. And then you also need mixing. It's not part of the triangle, but if you don't have mixing, if you don't have intimate contact, then you're not going to have a fire. So a lot of times we use that mixing effect to fight fires. And so we'll spray water mist on there. What is spraying? Like with the fire department, they show up with the water hose and they try to mist that water. What's going on there? There's two things that's happening. One, it's stealing the heat. Okay, these are water droplets, and it takes energy to break those hydrogen bonds. So the heat of the fire goes into evaporating the water, breaking the hydrogen bonds, and that is a large enthalpy. So it's endothermic to evaporate those drops. So they spray a mist of water on the fire, and it steals the heat. And then also when that flashes to steam, now you have steam, and the steam pushes back the nitrogen and the oxygen to some degree. So you exclude some of the oxygen. So it destroys the mixing of the oxygen with the fuel, and it steals the heat. And if you do this long enough, you cool the fuel down and you lose the heat, and you still have the oxygen and the fuel. You turn the water off, they mix, but the heat's gone. And so it doesn't relight. So that's how we fight the fires. You can use CO2. Also, it has a chemical effect. You start to, that's a product of the combustion. You see over here, CO2 is a product. And so you're sort of fighting the Gibbs energy of this reaction by flooding it with product, but it also excludes the oxygen and prevents mixing. The foam is definitely a physical effect. You're sequestering the fuel and keeping the oxygen away from it. So that's what they show, that they have on like fuel fires. So at the airport, whenever there's a plane crash and there's a leak of fuel on the runway, they run out there with the foam trucks, and they don't just spray water on it. In fact, that's not going to really help. If you just spray water on a fuel fire, the fuel is lighter than water, it floats. So then the water's underneath, the fuel's still on top, and you didn't exclude the oxygen. You spray foam on there, and that foam provides a barrier that prevents the oxygen from getting to the fuel. And then halogens, halogenated solvents. This is not used as much now. Well, gee, I wouldn't say that. It's in specialty situations. They have halon fire retardants. Because if you're in a museum and you've got a one-of-a-kind Rembrandt on the wall and there's a trash can fire, you're not going to go in there with a hose and spray down all the artwork just to put out this trash can fire. You drop a halogenated gas from the ceiling, heavier than air, excludes the oxygen, and smothers the fire. The carbon halogen bonds are high energy bonds. And so to break those bonds, it takes a lot of heat away from the chemical fire, the process of the fire. So that's why a lot of the perchlorinated and perfluorinated solvents are not flammable. So we use those in the cleaning industry to make mixtures. We'll have a flammable solvent and we'll mix in a fluorinated solvent to make it non-flammable mixture. And so that's what a lot of my research has been in the past, is trying to find azeotropic blends that don't separate when you heat them up and use for cleaning. There's a lot of regulatory interest in excluding those solvents now. They have unknown toxicity, but they're showing up everywhere. These fluorinated solvents, you may have heard of PFAS in the news. That's perfluoroalkyl substance. So you've got an alkyl chain, just like a CH2s, but you take all the CH2s off and put F2s. So perfluoroalkyl substance. A lot of these solvents are so inert, they're not acutely toxic, and they're approved for use in cosmetics. And so that's why we're seeing them everywhere. So perfumes and things that you spray on, these solvents are easily evaporated. So you can dissolve, say, a floral fragrant oil in these solvents, spray it on your skin, the solvent immediately flashes away, leaves the oil behind, and you smell nice. Okay, so these perfluorinated alkyl substances are everywhere. We're spraying them on our skin. So it's no wonder that they're showing up in water samples or even in our fatty tissues. And so there's some concern about them just being everywhere. And so now there's this regulatory interest in scaling back their use. But those halogenated substances have been used in the past, and in museums and things still used for flame retardants. When I was at Texas Tech, they had a pharmacy museum, and it was an old, like 1800s pharmacy. And on the wall, the fire extinguisher was this glass globe. It's an ampule about that big, full of this red liquid. And it said, "In case of fire, throw at base of fire." And it was a fire retardant grenade. Okay, and it was filled with carbon tetrachloride, which is not a very nice molecule. I think it's a carcinogen and pretty dangerous for you. But if there's a fire in the room, you would take this off and just throw it at the base of the fire, and it would splash this carbon tetrachloride on the fire and hopefully put it out. I mean, you only had one shot, right? And you throw it and run. So, but I thought that was a pretty extreme fire extinguisher. Now we have a lot better ones. There's not any in this room, but they're in the hall, I guess. So let's talk about this combustion continuum. Here's a lot of things that are going on with combustion on the left. And so the forensic application would be, arson fire investigation. In the middle, we have propellants. So gunpowder is not really just combustible, and it's not really an explosive. It's in between. It's called a propellant. So it propels the bullet. And then you have explosives, you have low explosives and high explosives, which are really related to the power output of the explosive. And so you have just combustible material, flammable material over here on the left, propellants, low and high explosives. And then over here on the far right, we have nuclear. And the thing I want to emphasize here is the difference really is the speed of the burning. And so in a fire or something that's combusting, you have a subsonic energy front. Okay, so the front of energy going through the material is subsonic. But then as you get into propellants, it starts to approach the speed of sound in the material. And when you get to an explosive, it's supersonic. So it's faster in the material than sound can travel in the material, which means it has to be an energy wave. It can't be conduction or convection. Conduction is just atoms banging into other atoms, which is what the speed of sound is. So if you send a vibration through air, I'm speaking, the shock waves going through air by collisions of the molecules in the air. If I want to break the sound barrier, I go faster than the molecules can transmit sound. And so I'm going through that air faster than sound. So you leave this shock wave in your wake, kind of like a boat on the surface of the water. You have that wake that comes out behind, and that's what the sonic boom is. Okay. For an explosion, this energy wave goes through the material faster than the speed of sound. So it's more like light than sound. So the energy flows through the material, and it's enough energy for a high explosive, essentially breaks all the covalent bonds. So if you think about a material, an explosive, a high explosive, if you send a shock wave through it and it breaks all the covalent bonds, you're way past the activation energy for any reaction. And so if you have hydrogen and oxygen in that molecule, it doesn't need to break any bonds. They're already broken. So you have only output. You have forming of water, forming of CO2, forming of nitrogen gas, and now you have all of these gaseous molecules at a really high temperature, and they expand rapidly. So the shock wave goes through material, breaks all the covalent bonds, chemical reactions, hot gas, expansion. And that's what happens in an explosive. In a propellant, it's a slow burn. It's still faster than burning, but it's a slow explosive burn. It's a deflagration. It's faster than combustion. So here's combustion. This is a beautiful image, I think. We've got the wood here. We've got the flame. The little bit on the end is typically some kind of phosphorus compound. There's red and white phosphorus. Sometimes they put in dyes and make it blue. They have a mixture. You see the Strike Anywhere matches? They got a blue tip and a white button on the outside. Those are two incompatible compounds that are encased in wax. So that's why they don't burn by themselves. You scrape them on some friction surface and you mix them. You break through the wax coating, and then the white phosphorus and whatever the blue compound is probably some sort of phosphorus as well, immediately start combusting in air. So that's why it really goes crazy. It gets enough heat to set the wood on fire, and then you've got fuel and you've got the wood. You got wood, fuel, and oxygen in the air, and they start to burn. So this blue flame here is the redox reactions, and mostly the hydroxyl radical. So that's blue light. So the blue light's coming from hydroxyl radicals. So it's the first part of the water formation. So oxygen is stealing the hydrogen from the wood, from the CH2s, and forming water. And as it forms water, it's forming excited state hydroxyl radical, which is emitting that blue light. But anyway, a lot of those reactions are giving off infrared and visible light in the blue end of the spectrum. If you don't burn all of the carbon to make CO2, like this is a perfect combustion, making CO2 in water. Sometimes it produces hot carbon. And those little clusters of hot carbon are what emit the yellow light. And this hot carbon soot gives off black body radiation. You guys have had PChem 1, so black body. So it's hot enough to emit in the visible range. Okay, so we can calculate the enthalpy of combustion for this reaction. And again, that would be an ideal case. That would be the most amount of heat delivered. If you're forming a lot of soot, you're delivering less heat. So we use these enthalpy of combustion calculations to sort of calculate a maximum or highest end amount of energy released from the fuel. So let's look at some of the math behind these. So we, in the thermodynamics course, we look at enthalpy of combustion, and I came up with this equation. I put in all of the enthalpy of combustion values from the CRC. So over several years, I built this database up, and I got up to 900 compounds. And then I thought, well, let's do 5 more, because there was like C60 and C70. Let's put those in. So I got to 905 compounds. And then I said, well, what if I just did a regression of the enthalpy of combustion? So here's the literature values. So how many kilojoules per mole for each of these molecules? And so my X values, remember doing regressions? Our X values were A, B, C, and D. What are those? Those are the number of carbons, hydrogens, nitrogens, and oxygens. So that's the X input. And the Y input was delta H of combustion. Okay. And I thought, who knows? I mean, if I've got more carbon, I should have more heat. If I have more hydrogen, I should have more heat released. More oxygen, we'll see what happens. And so I couldn't believe how well this worked. This is the enthalpy of combustion equation based upon A, B, C, and D. So if you have a compound like C60, okay, it's C60, H0, N0, O0. That's the formula for C60. So I'll put 60 in for A right there, the zeros for these, and add 32.1, and I get the enthalpy of combustion for C60. You see how you use the equation? Whatever molecular formula you have, you can calculate the delta H of combustion. And I was shocked when I took the calculated values from this equation. So this equation is over here on this axis, and literature is on this axis. It has a slope of almost 1, which means it's a 1-to-1 match, and the R squared is almost 1. So it's a really good model. Now you can see down here there's some scatter, and that would be easily understood, like the difference between CH3OCH3, which is dimethyl ether, and CH3CH2OH. Those have the same molecular formula. One's dimethyl ether, the other is ethanol. And in my model, there's no difference in the delta H of combustion. So there's going to be some scatter for those kinds of structural isomers. There's only one enthalpy of combustion calculated by my model, but the literature value shows a slight difference between those, but not very much difference. So that's an equation that you can use. There's a couple of, I think at least one calculation on the homework where you're asked about the enthalpy of combustion. Use this equation from the notes. Now, if we take that instead of per mole, we divide it by per gram of fuel, okay? And we can get that from the molar mass. And we know the molar mass based on the number and types of atoms. So A carbons times 12.01, B hydrogens times the mass of hydrogen, C nitrogen atoms times the mass of nitrogen, and D oxygen times the mass of oxygen. So we have the mass per mole, and we have the kilojoules per mole. So we end up with kilojoules per gram. So this would be called the specific heat of combustion. And notice that putting these compounds aside, it tapers off and reaches this roughly 40, 42 range. So about 42 kilojoules per gram. So that's a good estimate for combustible materials. What about all of these values down here? Those are oxygenates. This is the enthalpy of combustion in oxygen air, okay, that we're calculating. And if we've already got oxygen in the molecule, it lowers the amount of heat we get out. We're adding mass of oxygen, and we're not getting much heat for that because oxygen is the other reactant. And so it's like we already have combusted our fuel a little bit if it's already oxidized. So, acetic acid wouldn't be as good a fuel as just ethane, right? Because I've already reacted one of those carbons with 2 oxygens. So it's not going to give as much heat. Likewise, it doesn't make any sense at all thermodynamically to put ethanol in our fuel tank. We can know that right here. These are the numbers. Putting ethanol in your gas is pretty dumb from an efficiency standpoint. So there must be other reasons we do that. And one of those reasons is political. The lobbyists of the corn producers that can make bioethanol say, hey, we'd like another market for our ethanolic cellulose output. And so there's political reasons for putting ethanol in fuel. There's not any kind of scientific reason for it. And I'll stand by that. Okay. All right, so tools of the trade. We're using one of them, that is the amount of heat produced. But a lot of times, chemists, we're used to using moles. Everybody else that's not a chemist likes to use mass. Mass is the most basic measurement that you can do. And so a lot of these things are done by mass. And so we use these stoichiometric ratios and the system ratios. And notice that these are mass of fuel and mass of oxygen. So mass is preferred. So if your fire marshal comes into the room, they know the density of cardboard and paper and wood and all of that, and they can tally up how much combustible load is in the room. They may look at that desk and they say, well, that's like a 2.5 by 1.5 foot piece of wood. They add up how much wood there is. And they can tally how much heat the wood in this room will generate. And then they look at the sprinkler system, and they know the standard sizes of these little sprinkler heads and the pressure and all of that. And they know how much water that can put into the room. So they know how much heat the sprinkler system can handle. And if there's more wood in the room than the sprinkler system can handle, then the fire will leave the room eventually. If there's not, then the sprinkler system can maintain the fire to this place and save the rest of the building. So the fire marshal, when they do their inspections, they're thinking about this kind of thing. They're looking at what can the fire suppression system handle and what kind of combustible load do you have in the room. And so that's why a lot of chemists and other kind of scientists, if you go in their offices and you see piles of papers and books, a lot of times we get dinged by the fire marshal. So I might have one sprinkler system in my office, but I got all those books on the bookshelves, and they don't like that. They're like, you've got way more combustible load in your office than the sprinkler system could handle. Okay, that's going to burn slowly, so they kind of overlook it, but still, my office has more combustible load than the showers can handle. Okay, which is why they don't let us have candles in our offices. Yes. I'm not exactly sure on that. Yeah, there's a lot of, I don't know if they're regulations, but guidelines would probably be the right word for ingress and egress. And so like they know how many people can go through a doorway in a certain amount of time. And so if you get into a building and you have way too many people in there, then there's going to be a crush at the door. And it may be related to some of that kind of thing. They even would measure the walkways and so on at my last business, so that they know, so many people can go through a 72-inch width, less people can go through a 36-inch width. And so for a major exit of a room, there needs to be a 72-inch path all the way to the door. And so they get in and measure those kinds of things. But it may not be related to fire. It may be related just to movement of people. Yeah. But that's a good question. I don't really know how they come up with the occupancy of a room. Yeah. So let's do some of these mass calculations. So here's an example of the stoichiometric equivalent calculation. So what's the STE for methane and air? So look back here. This is the stoichiometric equivalent is this mass of fuel over the mass of oxygen. So what's the stoichiometric of methane and air? Here's the methane combustion equation. And so as a chemist, it can't be any easier. As a chemist, it's moles per mole, right? We have 1 mole of methane, 2 moles of oxygen. We're done. Look at how much work it is on this slide to get to the mass part, mass over mass. We do all these conversions into mass. So we got to convert moles of methane into mass, which is pretty easy. It's 16 grams per mole. So we're done with the methane thing. If we just multiply that by 16 grams per mole, we have the grams of methane. But how many moles of air will provide 2 moles of oxygen? Well, air's not pure oxygen. It's 21% of oxygen by mole percent. So in 1 mole of air, we have 21.21 moles of oxygen. So we need 2 moles of oxygen in our denominator here. Okay, so that's where that came from. 1 mole of air delivers 0.209 moles of oxygen, so we need 9.57 moles of air. Well, how much does that weigh? I mean, you're not going to find that on the periodic table. You'll find the individual pieces, but we've got to take into account all of the different pieces. So the nitrogen here is 0.781, and it's 28 grams of nitrogen per mole of nitrogen. And it's 28 because it's N2. You look at the periodic table, it's 14 for 1 nitrogen, 28 for 2. Then we have the ratio of oxygen, 0.209, times the mass of oxygen, 32 grams of oxygen per mole. And then we'll stop at argon. We're down here in the 3rd decimal place, 0.009 times 39.9 grams of argon per mole of air. So that just gives us that last decimal place. So we end up with 28.9 grams of air per mole of air. So 1 mole is equal to 28.9. Now that we have an equality, and this is the review from Chem 1, any equality can be turned into a unit conversion. If this is equal to that, then you can put them over each other and you're just multiplying by 1, right? Both sides are equal, you're changing the units. So we need 9.5 moles of air. We multiply by the molar mass of air. And you'll have this number right here on your equation sheet for the exam, so you don't have to worry about redoing this calculation every time. This will be one that you're given. So we end up with 277 grams of air needed to perfectly combust 16 grams of methane. So the mass of methane, that was 1 mole here of CH4 is 16 grams. The air mass is on the bottom. And so we take this ratio and we end up with 0.05. So about 5.8% by mass of methane. That's the perfect mix. So if we turn this gas thing on, we'd have to wait for it to reach 5% in air, and then we would be in a huge danger because it's the perfect stoichiometric amount in the room. Any kind of spark, we would have perfect mixing of fuel and oxygen at the perfect amount, and a spark would blow this room to smithereens. It would be devastating, okay? But I put a little bit in the room, it's way below 5%. So it's not even at the burnable range. Now, right up close it is, I could light that and it would have a flame because the ratio is good right there. But for the room to get to 5.8% would take quite a while, and I have to run it. So if you had a leak overnight, maybe it would reach the flammable limit, the explosivity limit. And so let's look at that. Would a 5 liter per minute gas leak reach an explosive concentration overnight? So overnight, 8 hours, 5 liters per minute. So let's compute that 8 hours over to minutes, so 60 minutes per hour, okay, and 5 liters per minute. So now we know, how many liters we have. So this is the same tool you used in Chem 1 many years ago, right? And you've used it since, obviously. So then what's next? We've got liters of gas. Okay. Somehow, what do we need to go next? What would you do? Like, we need to get from liters to something more useful for our equation, our methane equation, our stoichiometric amount. Yeah, we go to moles maybe. Let's just use like standard ambient temperature and pressure. So room temperature and 1 atmosphere. So room temperature and 1 atmosphere, this is the molar mass. So this one right here, V equals nRT over P. And so 1 mole times R 0.08206 liters, atmospheres per mole Kelvin. 298 Kelvin divided by 1 atmosphere. So all my units cancel, atmospheres are gone. This is a ratio here. The moles are canceled, Kelvin's gone, and so we have a liter here, gives us our volume. So 24, that gives us 24.4 when we put in all those numbers. That's the mass of 1 mole of methane at standard ambient temperature and pressure. So this would be called SATP. STP is at 0 C or 273 Kelvin, not 298 Kelvin. So that's why it's 24.4 and not 22.4. 22.4 would be STP. This is SATP, ambient. All right, so that's our mole. That's the number of moles, and the liters have canceled. And then we get out of moles because we're doing the mass of fuel, the mass of methane per mole. So far, all my units have canceled. We got to minutes, then to liters, then from liters to moles, and now from moles to grams. And then it's going to be a lot, so we're going to go to kilograms. So we have 1.57 kilograms of methane leaking into the room. Kind of a lot. Okay, it's an 8-hour leak. Now we need to calculate the mass of oxygen. So we need to know something about the room. Yeah, the room. Right? How much oxygen is in the room? What's the mass of the air? That kind of thing. And so that's where we have to, we just have to make stuff up, right? We have to estimate. So let's take a 2,000 square foot house. That's a smallish house. It's a moderate sized house with 8-foot ceilings. But again, you might, if you were to do this, if it was a handwritten problem, you would just say, I'm assuming a 2,000 square foot house and 8-foot ceiling. This is my assumption. Okay. It's a good one. Yeah. And so then we have to look this number up. So how many cubic feet are in a liter? So we would look that up. And now we've got liters per mole of air to grams of air. Okay, I'm going a little fast. I see you trying to keep up with me. And then from grams to kilograms. So this would be 536 kilograms of air in that size of house with 8-foot ceilings. So what's our ratio, right? This stoichiometric ratio for not the stoichiometric, this is the system ratio. 0.00239 kilograms of methane per air. This is the system. What we calculated before was the stoichiometric equivalent, STE. So stoichiometric equivalent, I should probably scratch this out and say sys, because we calculated the system. The previous page was the stoichiometric amount. The 5.8% was the perfect amount. This is coming out at 0.002. And so this phi is the ratio of those two. It's the system divided by the stoichiometric perfect amount. And we have about 5% of the perfect amount. If this were 1, then run. Do not dial the phone inside the house. Do anything that might generate a spark outside the house, because you're in danger. Okay, this will not catch fire. This is too lean. Okay, so even though that ran at 5 liters per minute all night long, filling a 2,000 square foot house, there's more oxygen than fuel, way more oxygen than fuel. And so you need to be able to do these kinds of conversions. It's just following the units and trying to get to where you want. We know we started with 8 hours of a 5 liter per minute leak. and we knew we needed to get to mass of fuel. And so we just worked our way that way. It's like making your way through the forest, you know. You want to go uphill or whatever, you just make decision by decision all the way there. Okay, so this phi is that fuel over oxidant. If it's 1, okay, that's when you have this explosivity limit. So perfect explosivity. And I'll say risk, right? That's when you're at the most risky. If you get too high, that we call that a rich mixture, okay? So when it's high, no combustion's possible because there's not enough oxygen. So if this thing ran for days and days and days, it would exclude some of the oxygen and fill the room with too much fuel, and there wouldn't be enough oxygen to maintain the combustion. And if it, in our situation, it was too lean, meaning we didn't have enough fuel, and so no combustion was possible because we didn't have enough fuel. There's going to be limits. So the lower explosivity limit and the upper explosivity limit, these are sometimes listed on the safety data sheets. So the safety data sheets for compounds, you can find those. Any chemical you're working with in the lab, you need to know what the safety data is. And so get on your phone, get on your computer, type in those numbers, type in SDS, benzaldehyde, you know, and you're going to get lots of options for the SDS for benzaldehyde, and then you can pull it down and you can see its toxicity, flammability, viscosity, all kinds of things. Now, one caveat to our calculation, right? That is, we calculated this as if it had perfect mixing, okay? So our assumption here, it is too lean, assuming perfect mixing. This is unlikely at night. Okay, what is the mass of methane? 16 grams per mole. What is the mass of air? 29 grams per mole. They have different masses, different densities. And so where's the methane going to go? Along the ceiling. And so this right here is what we would have. And we would have probably a rich mixture around the ceiling, a flammable mixture somewhere in between, and a lean mixture closer to the ground. And so even at this level of leak, we might still be in danger in the house at the ceiling level, right where when you flip the light on, you might generate a micro spark, or turn on the fan and you got a brushed motor and it generates sparks, and boom. Okay, so this can happen. This does happen occasionally. So again, that's why they put an odor compound in the natural gas, so that when you smell it, you leave the house. Now let's look at oxygen balance. So this is a totally different calculation. This isn't the stoichiometric amount for combustion in air. This is when oxygen is part of the molecule. So this is what we have for explosives. Explosives don't have to wait until they mix with the oxygen in the air. And neither do propellants, really. We have to put oxygen in the molecule so that it's already mixed. It's sort of pre-mixed. And think about that, you know, like nitroglycerin. We've got a glycerin molecule. So C, we've got an H. I'll just draw the ugly freshman Lewis dot structure here. Okay, glycerin has three OHs on it. But if we react those with nitric acid, we can nitrate it. And so it would be an NO3 group here. So that's nitroglycerin. Incredibly dangerous molecule. There's all those three nitrogens on there. The smallest little activation barrier in this thing explodes. It's been, you know, famous in a lot of movies, even back in the day with John Wayne. It was a great movie. Rooster Cogburn, him and Katharine Hepburn. I know I'm dating myself. I was a kid, honestly, when those movies were in reruns even. But they had it was used for mining. They would put nitroglycerin vials in there, and they would blow up the rock structure and mine. And it was a wagon that was crossing the river, and it tipped over, and these crates of nitroglycerin were floating through, and the bad guys were over there. And so John Wayne was shooting these crates of nitroglycerin and blowing them up in the water. Great Hollywood effects, you know. And as a kid, I was like, what kind of thing blows up when you shoot it with a gun? You know, that was really curious to me. And sure enough, nitroglycerin, that was accurate. It was so sensitive that if you dropped that box or whatever, it might detonate. Okay. So that limited its usefulness. And then along comes Alfred Nobel. Do you know what he did? Yeah. And that is nitroglycerin, but he mixed it with diatomaceous earth. Okay. And that was enough to dissipate the shock sensitivity of nitroglycerin and made it safe. You could drop dynamite and it wouldn't go off. You might even be able to like hit it with a hammer or shoot it and it wouldn't go off. You had to light it with a little blasting cap. And once you had the blasting cap, that was enough of an activation energy to get it to blow up. So they could put it into they drill the holes in the rock, put it into the mining areas, and then they could put a fuse and it would detonate those blasting caps and then blow up the dynamite. But you pull the blasting caps out and it's pretty safe. Okay. Pretty safe. Okay. And so why does it detonate? Well, it detonates because it has oxygen in the molecule. And so this is the calculation for oxygen balance. So here we have our regular, CHNO formula. And so we're going to form A moles. So here are the carbons. There's 1 carbon per CO2. So A is used directly for the number of CO2 molecules produced. B, they have to be used in pairs for water. And so whatever number of hydrogens you have, you divide that number by 2, and that's how many moles of water you can form. And then the C is used to form nitrogen. Again, it takes 2 of those to form a nitrogen molecule, so it's C over 2. And then do we have enough oxygen is the question. Because the oxygen has to take into account the amount used for the CO2, okay? And it has to take into account the amount of oxygen used in the water. So it's B over 2 for the waters, it's 2A for the CO2s, and then whatever we have oxygen here, we have that minus what is consumed by the CO2 in the water. And then we're dealing with moles of oxygen, O2, and so we divide that value by 2. And so this is the nitroglycerin equation. We have 3 CO2s, 5 over 2 waters, 3 over 2 nitrogens. You really don't even have to calculate the nitrogen because it's not related to the oxygen balance. And then whatever left over, 9 moles of oxygen atoms divided by 2 to make the O2. And so when we calculate this, we get a positive number here. We get a positive oxygen balance of 0.25 moles of oxygen. Now, if you look at this equation, and every year I look at it and I go, that doesn't add up, right? It's 9 moles of oxygen. So 9 minus 6 is 3. 3 minus 2.5 is 0.5. So I have 0.5 moles of oxygen, but this is O2. So that would form 0.25 moles of O2. So it does balance out. The point is for nitroglycerin, we have a positive value of 4%. So we have 4% more oxygen than the perfect amount of oxygen we need. So it's ready to go. Now it's all formed in nitro groups and the CH bonds and everything. But once this starts to release energy, remember that detonation shock wave goes through and breaks all the bonds. So now all the bonds are broken, and those nitrogen atoms can form a really stable nitrogen with a triple bond. Think about how stable that molecule is, okay? If it's given a choice, it would rather form N2, okay? And it does have a choice because all the covalent bonds are gone. It's as if you took your model kit, broke all the atoms apart, set them on the table, and said, now make the most stable atoms and molecules you can. And so you're going to grab the nitrogens, and you're going to form a triple bond of nitrogen, you're going to set that aside. Then you're going to form water, set that aside. You're going to form CO2 and set that aside, and you still got 4% of your oxygens left over. So you have plenty of oxygen to form all of those stable compounds. TNT, we know about trinitrotoluene, it does not have enough oxygen. So when we do those calculations, these pieces are larger than D. Okay, D is only 6. And when we subtract 6 minus 14 and minus 2.5, we end up with a negative 5.25 moles of oxygen. Okay, converting that to mass and doing the ratio, we're 74% low. It still explodes, but it would be better if we had more oxygen put in there. And so sometimes to juice up TNT, they'll add in an energetic plasticizer or something like nitroglycerin to provide a little bit more oxygen. And so you can take TNT and you can spice it up by making some other kind of composition. And that's where all these different explosive compositions come from. So plastic explosives are not just a single explosive sometimes. They have other components in them. The plastic part is just to hold them all together. You use different plastics to make them with different properties. You can make hard plastics where it's really hard, kind of like this plastic on this plastic stapler. And you can make pastes, things that can be pushed and molded into shape. So they have all kinds. And that whole area is called explosive engineering. You could be actually an explosive engineer. And that would be pretty cool. Okay, let's talk about fires. We'll come back to explosives when we get to the molecules part. Okay. So this is, let's just talk about a candle for now. So the wax, I would say the wax doesn't actually burn, it decomposes. So when you light a candle, you put the heat on there, you melt enough of the wax and it comes up the wick, and then it gets hot enough to decompose. And so these are I would say wax bits. Decomposed parts of the molecule that are burning. Okay, and when they burn, they generate heat. Some of that heat goes down and melts more wax, and then the wax flows up the wick, decomposes and burns. And so we're actually burning the gas above the wick, and that's why you see the little shape of the flame. It's the gases that are burning the decomposed wax bits. But the temperature of the wax is at this melting point. So this melting point and the delta H of fusion, that's what keeps the glass of the candle and the base of the candle and everything from scorching the countertop, right? Because it's held at the melting point of wax, and that's not enough to mar the surface of whatever the candle's sitting on. You ever think about that? You got a flame there. How come it doesn't leave a scorched ring on the top of the counter that you've got it set on? Okay. It will if you let it all melt. So if the whole wax candle melts, and this may have happened to you, where the whole thing melts, then the liquid starts to heat up. And then the liquid and then the glass, along with that liquid, can get up to hot enough temperature that it'll start to mar the surface underneath the candle. The flexibility of that glass, it might be poor glass, and it might crack or break. Then the liquid flows out all over, and if the wick falls over, it might catch the top of whatever it's sitting on fire. So this is why candles are dangerous, and why you don't leave them unattended, because if the liquid completely melts, then you start to heat the liquid, you start to heat the glass container or metal container, and then you might catch the surface of what it's sitting on fire. But the melting point is what keeps the candle safe. Until that candle all melts, then it's pretty safe. And even then, it could reach not so much for wax, but for other fuels, it will also pause at the vaporization temperature, the boiling point of the fuel. Now, waxes, they're just, the chains are just too long and they won't melt. They'll decompose. But if you have a fuel, let's say you're an arsonist, you want to pour fuel on this carpet in the living room and light it on fire, you're probably not going to get away with it. It's going to be detected as arson because the boiling point of the fuel will keep that carpet from decomposing. And so this is what we see in arson. So this is a fuel fire So you pour gasoline on carpet and light it on fire, and it's burning vigorously, and you see that, but this piece of carpet in the middle is protected by the boiling point of the fuel. And so if you're an arson investigator, that's what you go for. If someone's dumb enough to try to burn something down, or commit arson, and try not to be detected, you're going to find evidence of whatever fuel they use, whether it's gasoline, diesel, white gas, whatever. You know, and you can find the trace elements in that, and you might be able to find out even where they got it. We'll talk about that more. There's a whole lecture on arson. Okay, heat rises. That's our number one principle in terms of fire detection. So and fire analysis. So like if I were to, I don't know, put something in that plug that's going to create a fire. Let's say I was trying to be an arsonist, and I put some kind of substance that's going to short out that plug and catch the house on fire when that plug's energized. And let's say it did catch the room on fire, I would see that area around the plug is really, really charred and burned, and then I would see the heat rise. And so I could come into this room, let's say we got it put out, I could just follow the black charring back down to the source. Okay, and so it'd be easy to detect that it started at that plug. It might be hard to prove if it was arson or not, but it would certainly start. So you have this V, typically you have a V from the source of the fire. A lot of the material in the room is going to be disturbed, removed, destroyed by the fire department. So it's a sort of a back and forth, irritation, like they poke fun at each other, the arson investigator and the fire department. Okay, so the arson investigator calls the fire department the evidence destruction team. So they come in and they just blast everything out the front door and then spray it in the yard and like with their hoses, and then it's all done. But all your evidence is now in the front yard, all mixed together with non-evidence, and it's just a big wet mess. Okay, so a lot of times you have to look at the room, you have to look at the ceiling, you have to look at the walls. Hopefully the structure hasn't completely fallen in, and it'd be difficult to determine if it was arson or not. So from combustion to detonation, we have to go through deflagration. So this is typically determined as this DDT, the deflagration to detonation transition. So when there's just a flame, something burning like a candle, there's no pressure buildup. Now it's kind of hard to get pressure buildup in a candle or in a flame like that. What would you want to do if you wanted to build up pressure? Yeah, seal it up, put it in a box. But what does that do to a candle? It excludes the oxygen, and so then you're not going to be able to get pressure buildup if you exclude the oxygen. So that's why you need oxygen in the molecule itself. If oxygen were mixed in with the paraffin, then you could put it in a box and you could get the pressure to rise. And if the pressure rises, the heat goes up and you might get an energy wave. If that energy wave starts to go through the material in a controlled fashion, you could get deflagration, vigorous burning. If that shock wave goes faster than the speed of sound in the material, then you can have detonation. So you have breaking of all the covalent bonds nearly instantly, and then you have a reaction, and then you have an explosion. So propellants have this controlled pressure buildup. So propellants are used in gunpowder, and rocket fuel. Okay. Now, some rocket fuels are mixed liquids, like Elon Musk's rockets. You know, he has the fuel and the oxygen spraying into the motor in a controlled rate, and so that's a binary mixture. They're mixing it in the engine, but this would be for like a solid rocket booster or a solid rocket or propelled grenade or something like that. So these propellants would be something that you might come across in a forensic situation. If we can build up pressure, then we can have this explosive train. So you might have a detonator that gives you a small energy output, but it's enough to light a higher energy output. So low explosives are typically sensitive, and we can set them off with a spark. Shock is a mechanical shock. Okay, so this means impact. Not like a shock, like you get an electrical shock. That would be spark sensitivity. Heat sensitivity or friction. We have some of those for 4th of July, right? The little poppers, you pull them apart and the friction sets off the pop. Okay, so that would be friction initiated. Matches, again, you mix those compounds and they automatically go off. And then high explosives are chemicals with a high oxygen balance. And then you need to use a high explosive to get the nuclear materials in a supercritical mass fast enough. Okay, so for every nuclear detonation, you have to have a chemical explosive detonation. There's no way to make a nuclear detonation without first having a chemical detonation. Okay, at least, well, they've never come up with one. I'll just say that. Okay, maybe there is, I don't know. So here's how we start the explosive train with these different kinds of detonators. You can use a flame initiated with a fuse. They have this pyrotechnic ignition mix. So this pyrotechnic ignition mix, this would be a propellant. Then you have a primary explosive, something that's a little more sensitive. In this case, it would be heat sensitive, or maybe pressure sensitive. And then you have the output explosive, which does the most work. Okay. And that output explosive puts it into the material, and then the explosive train can propagate. We also have low voltage, high current initiated, something like a car battery or maybe even a 9-volt battery. And this is called an electric match. This is some of the things that worry me, because you can get this electric match at Hobby Lobby. Why would they sell that? I love Hobby Lobby, but why are they selling electric matches? Yeah, exactly. Model rocketry. Yeah. Model rocketry is great. I mean, it has propellant right there in the little cardboard tube, and you got to set it off. So you have the electric match, sets off the pyrotechnic mix, you got a rocket. You know, so that's fantastic. Okay. You get into military uses, and then we have these high voltage initiated. So these are the safest ones down here. Safe, but also suspicious. Military, right? These exploding bridge wire detonators. You need a high voltage. What does the bridge wire mean? Well, you have the leads that go in, and they have a tiny little gold wire in between the leads, and so you put enough voltage through there, and the gold evaporates. When it evaporates, it creates a thump, right? All of that gold slams into the initiator explosive and detonates it. It's enough activation energy to get it to go, and then you started the explosive train. A slapper type, instead of gold, they just have a plastic film. Same kind of thing. Enough voltage goes through, it sets a shock wave of this evaporated plastic that slams into the metal, slams into the initiator explosive. Okay. Once you get it started, then you have the deflagration to detonation transition. So D, D, T, and we have this shock wave that builds up. And once you have that shock wave going, then you can put that into an output explosive. Here are some of the compounds that are in these detonators. So these are the most sensitive ones. These top three are very sensitive. So this is lead stiffnate. So stiffnate, that's kind of a weird sounding compound. It's this benzene ring. It's got nitro groups. So these are, and here's some vocabulary for you that I require you to know. So this is a nitro. And it's hooked to an aromatic. So that's a type of explosive called a nitroaromatic. Notice this is not a nitro. Even though the word says nitro, this is a nitrate. So don't be confused. Nitroglycerin isn't actually a nitroaromatic. It's a nitrate, an organic nitrate. NO3. So NO3 is a nitrate, NO2 is a nitro. Okay. You could take cellulose and react those OH groups with nitric acid and make nitrocellulose. We still use that in gun cotton. So our artillery, think about if you want to throw a heavy artillery shell, like 100-pound shell, 5 miles or 2 miles, a long way. I don't remember how far they go. You want to use something that's going to give a lot of power, but it can't be instantaneous power. It needs to be a propellant. It needs to build that pressure slowly, because that shell is going to go from 0 miles an hour to pretty fast by the time it exits. But if you have a detonation instantly, you're going to blow the gun barrel up. So they use nitrocellulose. They put these they look like marshmallows that are about this big. They put the shell in, 2 or 3 little pillows of nitrocellulose, and then they close the breech, pull the string, boom. It lights that nitrocellulose, builds up pressure. What an explosive engineer would be called slowly. But from watching a gun, the artillery, it yanks back. It looks pretty fast to us. But in terms of a detonation, it's slow. It's a propellant. It burns slowly and pushes that shell out the end. If it were a detonation, it would blow the gun barrel up. The breech would explode. Okay, and then there's PETN, pentaerythritol tetranitrate. So it's 1 carbon surrounded by 4 CH2ONOs. And then we have the high explosives, the main explosives. So here's the chemistry of these. These are nitramines. So it's an amine and a nitro together. So look at the name, recognize that that's a nitramine. Okay, this one has both nitrophenol, nitramine. Can you recognize the pieces? Here's the nitroaromatic. Okay, there. And here's the nitramine stuck on the edge. Okay, so tetryl is both a nitroaromatic and a nitramine. Picric acid, trinitrophenol. So again, this has aromatic nitros. Trinitrotoluene, also aromatic nitros. So it was a toluene molecule that had been nitrated 3 times. And then this is the least sensitive molecule. At least the least sensitive that I know of. Maybe there's others. And this is TATB, so trinitro triamino or triamino trinitrobenzene. So this is still a nitroaromatic. Okay. So HMX and RDX are nitramines. Tetryl is both a nitro and a nitra. So nitroaromatic and a nitramine. And then all 3 of these are nitroaromatics. So for our composition B or other kinds of plastic explosives, there are different mixtures of these main charges. Okay. And so this is the rest of the explosive train. You have the detonators, we talked about those. They go into a booster, which takes the shock wave from the detonator and ramps up its energy so it goes into the main charge. And that may be all you need. Maybe you need just a main charge. You don't need a booster. Other times you need a booster and you need a main charge. The explosive engineer is the one that decides how to build up this explosive train, depending upon what they want to do. Do they want to break a grenade or an artillery shell? It's going to be a certain thickness of the metal and so on. Do they want to push one mass of uranium over to another mass of uranium and make a supercritical mass and make a nuclear detonation? Then they would engineer it that way. Do they want to put tritium gas in the middle and fuse some of that tritium to make helium? Then you get a fusion piece, and that's the thermonuclear piece. So this would be a hydrogen bond. So fusion would take place in the middle of a fission reaction. So that's as far as we've gone. That's the power of the sun, actually. The energy in the sun is fusion. So we can go from an electric match from Hobby Lobby all the way up to the sun's energy using an explosive train. And it takes a fair bit of engineering to get this to work. So that's what keeps us safe. Not any Joe Blow in his garage can get this to work. Okay, thank God. Okay. Now, for you as a forensic scientist, where's the evidence? The most volatile explosives are in the detonators. So I'll put up here detectable. Okay. The radiation from the nuclear devices is detectable too. So tritium is a radioactive gas with a 12-year half-life. Uranium's not that radioactive, actually. So you probably wouldn't detect that, but you might detect tritium, and that would be extremely rare, but extremely scary too. But the detonator is the Achilles heel in almost all explosives because it's the smelliest, and you can sniff for it. So you can get sensitive ion mobility spectrometers to sniff for PETN and other kinds of sensitive explosives. After the fact, after there's a detonation, not all the explosive is consumed. And so you can always find residual explosive at the site of the detonation. Most of it comes from right here where I've got it circled. Notice this shock wave has to turn this corner, and it can only turn so sharp. And so this part of the explosive is unburned and left behind. So if you can find any of that residual explosive, then you can know what kind of device, how it was constructed. Also, rarely is the fusing and firing destroyed. If they used a cell phone or some kind of timing device to detonate it, that can be crushed, but it's rarely destroyed. So you typically find the thing that set it off too. So there's going to be explosive residue on there. There might even be other kinds of evidence telling you where that device was used and where it was from. And so that's your evidence as a forensic scientist. The thing that set it off and some of the detonator or main charge explosives should be left behind. Probably not in a nuclear explosion. Okay, but again, you're going to have so much radioactive evidence in that case, and you're probably not going to be the one analyzing it unless you're working at Lawrence Livermore or one of our national labs. But hey, I'd love for you to find your way to one of the national labs. Give me a call if you end up there. That'd be great. Okay. We're out of time, so I'll take any questions afterwards. You can come up.